A 4,000-ton machine was stopped by a single pipe. Not a massive rock, not a system failure, one pipe. And it froze a $143 million project underground for 2 years. The machine was called Bertha, 17.5 meters wide, 5 stories tall, built to chew through solid ground like it was nothing. And yet, it couldn't move, because deep inside that machine, one system failed. And that's the part most people never see. Because a tunnel boring machine isn't just a drill, it's something far more fragile. And by the end of this video, you'll understand why even a machine this powerful can't move at all, unless 3 systems work perfectly together. Most people imagine a giant spinning drill. Point it forward, turn it on, dirt comes out. Simple. But that's not what this is. This is a 100-meter-long moving factory, and it's doing 3 jobs at the same time: cutting the ground, holding the earth in place, and building the tunnel wall behind it, all at once. If even one of these stops, everything stops. The easiest way to understand it is to think of a syringe. The cutterhead is the needle, the soil is the fluid, and the hydraulic system is the plunger. All 3 have to move together, or nothing moves at all. At the very front of the machine is a massive spinning wheel, the cutterhead. But it's not a blade. It's covered in dozens of steel disc cutters, each one designed to crush rock under extreme pressure, not cut it, crack it, like pressing a rolling pin into a hard biscuit until it fractures. And this is where things get interesting, because the machine doesn't remove all the soil it cuts, it keeps it. Right behind the cutterhead is a sealed chamber filled with that excavated material. Engineers call it muck, but that muck isn't waste, it's support, because the ground outside the machine is trying to collapse inward all the time. So the machine carefully controls the pressure inside that chamber to match the pressure of the earth outside, perfectly. Too little pressure and the tunnel collapses. Too much and the ground above starts lifting. Buildings crack, roads shift, everything above you moves. And all of that balance comes down to one component, a screw conveyor. At the bottom of the chamber, speed it up, pressure drops. Slow it down, pressure rises. That's it. One rotating screw, controlling the stability of everything above your head. Get that wrong, and the entire system fails. But here's the part most people never think about. Those disc cutters on the front, they wear down, just like the tread on a tire. And when they do, someone has to replace them. But out there is not outside the machine, it's inside the ground, under pressure. At the very front, the pressure in that chamber can be higher than what a scuba diver feels 30 meters underwater. So engineers do something extreme. They create a pressurized airlock inside the machine, and the crew has to enter it, slowly, over hours, their bodies adjusting to the pressure. Then they crawl forward into the cutting chamber, surrounded by mud, steel, and force. They replace the cutters by hand, one by one. And when they come back, they can't just walk out. They have to decompress, slowly, because if they don't, nitrogen bubbles form in their blood. Decompression sickness, the same thing that puts deep-sea divers in the hospital, sometimes worse. A single maintenance job can take an entire day. So the next time someone says this is just a drill, remember this machine comes with its own diving protocol. Now step a few meters back, behind the cutterhead. There's something even more dangerous. Nothing. No support. Just raw ground. Which means, while the machine is cutting forward, it also has to build the tunnel wall at the same time. Each section of tunnel is built from massive concrete segments, 5 to 7 pieces, each weighing several tons, placed one by a robotic arm, until the final piece, the key segment, locks everything into place. And here's the counterintuitive part. These segments aren't held together by bolts, they're held together by pressure. The weight of the earth pressing inward is exactly what keeps the tunnel standing, like a stone arch. But there's a catch. Between the tunnel wall and the ground, there's a tiny gap, and even a few millimeters of empty space can cause buildings above to crack. So the moment a ring is completed, grout is injected into that gap, filling it completely, sealing everything in place. This system has to be perfect. No delays, no gaps. Because if the cutting moves forward before the wall is ready, the ground wins. Now the final question. How does a 4,000-ton machine actually move underground? It doesn't roll, it doesn't crawl, it pushes. A ring of hydraulic cylinders presses against the tunnel wall that was just built and drives the entire machine forward, one segment at a time, like an inchworm. Each push installs exactly one new ring, then resets, then pushes again. But here's the part that's hard to believe. Each of those cylinders can push with a force of around 1,500 kilonewtons. That's like 15 fully loaded trucks pressing on a single point. And there are dozens of them working together. Total thrust can exceed 2,000 tons. Now imagine pushing a sofa across a carpet. Push from the center, it moves straight. Push harder on one side, it turns. That's exactly how this machine steers. Operators don't use a steering wheel. They control a single dot on a screen, the center of thrust. Move the dot left, the machine turns right. Move it up, it climbs. A tiny shift, controlling a 4,000-ton machine, bending through solid ground. Now imagine doing that for kilometers. 3, 5, sometimes more. Under buildings, under rivers, through changing soil, and still hitting a target within a few centimeters. That's like threading a needle from one end of a football field to the other, blindfolded, with a machine the size of a building. To do that, the machine uses a laser guidance system. A beam is fired from the tunnel entrance to a sensor inside the machine. The sensor reads where the beam lands and calculates how far off course it is. But here's the problem. Tiny errors grow. A 1 millimeter mistake at the start can turn into an 18 millimeter error at the cutterhead. And underground, that's enough to cause serious problems. So the system is constantly recalibrated. And when GPS disappears, gyroscopes take over, using the same physics that keeps a spinning wheel stable to track direction in complete darkness. Now go back to Bertha. That single steel pipe didn't destroy the machine. It damaged a seal that was holding pressure inside the cutting chamber. And the moment that pressure balance was lost, everything else failed. The ground couldn't be stabilized. The cutting couldn't continue. The tunnel wall couldn't keep up, and the entire system stopped. Not because it wasn't powerful enough, but because the coordination was broken. That's what makes a tunnel boring machine different. It's not about strength, it's about synchronization. 3 systems working perfectly at the same time. Break one, and even a 4,000-ton machine becomes completely useless. If you want to see more breakdowns of how massive machines actually work and what happens when they fail, hit subscribe. Because the real world isn't just powerful, it's precise.